Let's take a look at actually how are we going to construct our confidence interval for one population mean. The assumption in this lecture is that we know the population standard deviation, somehow sigma is known. Okay, so that's what our assumption is. Now, so what I have here is the other assumption. Our assumption is that the random variable x follows a normal distribution with a mean mu, which is going to be unknown, and some deviation sigma, which somehow it's known. Now, it could be known because of, let's say, prior research, prior study, because of our somebody else maybe has done this, or we can just simply make an assumption about it. So later on, we're going to relax that assumption and you'll see what happens. And so we have the assumption of normality, or the sample size is going to be at least 30, and it doesn't matter whether the distribution is normal or not. We have it from any distribution. And remember, this is the direct consequence of central limit theorem. Central limit theorem says that if you sample from any distribution, the sample size should be at least 30. Now, in our previous lecture, we did mention that the mean of x bar is going to be the same as mean of random variable x. And remember, that is going to be unknown for us. Okay, so this is usually unknown and needs to be estimated. Okay, and then what I have here is the sampling distribution of x bar. You split it into the units of a standard deviation, sigma x bar. And like I mentioned earlier in the previous lecture, if you go 2 deviations above and 2 deviations below, that interval is 95.44%. Okay. Now the z-scores that correspond with these are 2. The number that's attached to sigma x bar is 2. That comes directly from the z-score. 0 here is 0. The z-score is 0 at the center. And the -2, so the z-score is -2. Okay. Now we can generalize this, by the way, to any confidence level. So our confidence level is actually 1 minus alpha. Okay, that's what our confidence level going to be. And that's what the inside area is. Now, 1 minus alpha is our confidence level. Remember, the area under the entire distribution is 1 because this is a probability distribution. So if we have 1 minus alpha in the middle, that means by symmetry we have alpha over 2 on the upper, alpha over 2 in the lower tail end of the distribution. And again, here the z's are reflected from what's above here. I generalized them. And now we are in a position to actually do confidence interval for any confidence level, not just, let's say, 95.44%. And here is our formula for this. And I have the formula for you because it's in the book, but we actually use Minitab, and you don't need to know the formula in the Minitab. We just run the procedure. But here's the formula: x bar plus or minus z sub alpha over 2 times sigma over root n. Okay, this z sub alpha over 2 is right up here. That means a z-score, so the area to the right is alpha over 2. That's what that is. And what is alpha here exactly? Remember this symbol here, the symbol we have, this is called alpha. That's what that symbol is. Alpha, at this point, I call it the uncertainty level associated with confidence interval. Later on, when we talk about the hypothesis test, we're going to have a different interpretation of alpha. Okay, but for now, we're just going to call it the uncertainty level associated with the confidence interval. And our procedure that we're doing is called the 1 mean, 1 mu, z interval procedure, because our multiplier right up here, see, that's a z-score. For that reason, this is called the z procedure. Now, here are the assumptions again that are important for this work that we're about to do. We have a simple random sample, and really we can say, simple random sample with replacement from a finite population, or without a replacement from an infinite population. The second assumption is normality of the population or large samples. Remember, large doesn't have to be in the hundreds or thousands. For central limit theorem, 30 is large enough. And finally, the assumption sigma is known. And the formula that you see here is precisely the formula I have up there. Okay. And your confidence interval is going to be exact if you do sample from a normal population. Otherwise, it's approximate. Now, the values of z sub alpha over 2, I have actually written down some of the values for you here. Okay, so right in here, for example, if the confidence level is 80%, the z that goes with it is 1.282. I actually got these from a table, but we can also get them. Remember, we can find area under the normal probability distribution from Minitab also. But once we have these scores, we don't need to reinvent them every time. So in other words, for the 90% confidence interval, the z-score is going to be 1.645 always. So these z-scores do not change based on these confidence levels. For the 99%, the uncertainty level alpha is 1%, and half of that is going to be 0.025. Actually, I see an error in here. Let me fix this one. This is alpha over 2. It's going to be 1/2 actually. Okay, so that's going to be where's my pen? There it is. It's going to be 0.5, right? Because it's alpha is 1%. Half of that is going to be 0.5%. And the z that goes with that is 2.576. That's the z-score that goes with it. Okay. Now, what factors influence the width of a confidence interval? That's what we're going to talk about. Here I have the list of it. And by the way, generally speaking, we would like to have narrow confidence intervals. The narrower, the better. Because remember, we want to make a statement about the mean. So if I say, for example, the average rent in a given zip code ranges from $1,000 to $5,000, that's not really informative because there's such a wide range. So it would be much more beneficial and helpful if I said the average rent in a certain zip code is, for example, $2,000 to $3,000. That would make more sense. And it's also a better information. So generally speaking, again, in general, we would like to have narrow confidence intervals. So how can we actually accomplish or achieve a narrow confidence interval? Well, we can do it based on investigating what's to the right of the formula for confidence interval. This part z alpha over 2 times sigma over root n. Now, because of the relationship between z, sigma, and square root of n being in the denominator, so as sigma increases, this numerator increases, then the length of the confidence interval is directly proportional to that. So does the length. So that's not a good thing. Therefore, what we would like to do is to decrease the variability in data, and that causes a lower, a narrower confidence interval, if you will. What if we increase our confidence level? That's your 1 minus alpha. Well, the greater the confidence level, and you can see that up here. See what happens to your confidence levels, 80, 90, 95, 99. As you increase it, look what happens to your z-scores. They're getting bigger, bigger, bigger because you're pushing out into the tails of the distribution. So as confidence level increases, so does the confidence and the length of the confidence interval. And I have that here. As your confidence level decreases, so does the width of your confidence interval. Now the things I have in highlight are the corrective or remedial actions that will reduce the length of the confidence interval. They result in a narrower confidence interval. And what else can we do? Well, sample size n. In fact, the length of the confidence interval is inversely proportional to the square root of n. It means a reciprocal relationship with the sample size. In a reciprocal relationship, the bigger the denominator, the smaller the whole fraction gets. So, as the sample size increases because it's in the denominator, then the length of the confidence interval will actually shrink, which is a good thing. And if you drop your sample size, the length increases. All right. Now, here is an example that I actually have done in Minitab, and we will actually go to Minitab and do this exercise together so you can see how it's done. Okay. Now, in this exercise, or in this example I have, well, suppose a U.S. car rental firm wants to estimate the average number of miles traveled per day by each of its cars rented in California. Notice how inferential that statement is. We want to know the average, that's mu, miles traveled for all the cars. Okay, this is again the number for its cars that are rented in California, all of the cars. And you can kind of see the trouble in trying to collect this information. So what do? They take a simple random sample of 20 cars. Okay, so n is 20. And the sample shows the sample mean, that's your x bar, is 85.5, right? So that's what that is, 85.5 miles. And assuming the deviation in the population is 19.3 miles, suppose we can ask that from that rental company and they know that from prior records. Okay, and we want to compute a 99% confidence interval. So our confidence level, our 1 minus alpha here, is 0.99. Okay, and as you can see, there you go. Pretty simple. Without knowing that formula in Minitab, we're doing a one sample z in a confidence interval. Sample size is 20, mean of 85.5, and the confidence interval runs from 74 to 97. Okay, now this is what I mentioned, that SE mean. SE here stands for the standard error. Okay, so when we say SE, again, SE means the standard error. That's what that is. That's actually sigma over root n. That's what that number is. So if you take your sigma, which is 19.3, and divide it by square root of the sample size 20, I bet you're going to get 4.32. That's how that's calculated. Okay. And there's your confidence interval. So it's pretty simple, actually, using Minitab. Let's look at our second example, and then we will go to Minitab to do this. In our second example, and let me just jot down our confidence level here, was 99%. Okay. I'm keeping track of it, jotting down on my piece of paper. Okay, in our second example, let's say, suppose the researcher wants to estimate the average commuting time in minutes to work. So this is commuting time to work, from home to work, one way, not round trip, in San Diego. And then they take a simple random sample of size 16 commuters, and the commuting times are recorded, assuming the deviation is 5.124 minutes. We want to construct a 95% confidence interval for this one. Okay, so for the commuting example is 5.124 minutes, and we want to do a 95% confidence interval. Sample size was 16. Okay. And the assumption is that the population distribution is normal. That's the distribution of all individual commuting times, hundreds of thousands of them. And there you go. So according to Minitab, the confidence interval this time is now from 24 to 29, almost 30 minutes one way. Okay. Now the reason I have the second example is because we're going to run this procedure two different ways. If you note the difference, the key difference, other than the word problems being different, the key difference between example 1 and example 2 is that in example 1 we actually do not have the data. We have summary information. Summary means somebody gave us the means, they gave us the sample size, and they gave us the deviation. We don't see the actual scores, those 20 scores, okay, the 20 raw numbers. Whereas in number 2, example 2, you're looking at those individual commuting times. And there you go. So let's actually go to Minitab and try to run this. So if I remember, I still have a Minitab up and running. Yes. Okay. So as you can see, I've already populated this column with times. Those are the 16 commuting times for example 2. But let's actually do example 1. So we want to do a confidence interval for the mean. You're going to go to stat and then go to basic statistics, and you get a whole list of stuff. See all of that? This is practically where we're going to be for the next 2-3 weeks. Okay. And so in basic statistics, go down to one sample Z. Okay, that's what we want to do. One sample Z procedure. Click on that. Here's the dialog box. Now, if I click here on the drop down, it says, okay, it's asking me if I have summarized data or do I actually have data in a column. Remember, in example 1, we didn't see the data, we had summary information. So I'm just going to go summarize data. It says, okay, well, what was the sample size? And if you remember in example 1, the sample size was 20. So I'm just going to type 20 here. Our sample mean was 85.5. Just going to type 85.5, and this known standard deviation is 19.3. See, we inputted summary information. Now, we do not want to perform a hypothesis test. Let's go to options here. Click on the options, and there you go, confidence level. We're going to change that to 99. Okay, so 99. And don't worry about this part, this dialog box here, that's for hypothesis tests. We'll look at that in the next lecture. Okay, and that's it. Okay, and then okay again. And you will see what I had earlier. Okay. And there you go, the mean 85.5, and those were the confidence limits. Oh, the 74, by the way, that's the lower limit. 97 is the upper limit of that confidence interval. Okay, so pretty easy, huh? Now let's do our second example where we actually have commuting times. And let me just pull this up so you can see. You see, these are the commuting times I already input. And you can, there you go, see the whole thing now. This is the entire data. Okay, shrink it. Now, we want to do, again, a confidence interval, this time in 95%, but the difference is I don't have summary, I have the actual data. So you go stat, basic statistics, and then go to one sample Z, and then you don't need to put these numbers in. You drop down and you see that one or more samples each in a column, because that's what we're going to have. Now if you click, just left click once inside of this box once, it gives you the column where the data appears. This is where the data is. So you can left click once, select if you like, or if you double click on that, it will import it itself. Now, what is the known standard deviation for this exercise? Remember, these were commuting times. It was 5.124. Okay, and options, The confidence level for this exercise I made was 95%. Okay, and we're good. We don't need to give it the sample size. We don't need to give it the sample mean. Minitab has the data. It will calculate those directly itself on its own. Hit OK, and there you go. One sample Z, confidence interval for time in minutes. And these are the specifics. The average time was 26 minutes. And the standard deviation is almost 5. The standard error, again, that's sigma of x bar, is 1.28. And our confidence interval runs from 24 to 29. Okay, so we are 95% confident the true average commuting time lies somewhere between 24 and 29 minutes. And the other way, by the way, this idea of confidence interval can get a little technical. Here's really what this means. If you take repeated samples of size 16, and build the confidence interval, and then go out, get another sample of size 16, build another confidence interval, and another sample, and another confidence interval, and. Do that forever. In the long run, 95% of those confidence intervals will contain the true mean. Now remember, that's kind of a pie in the sky. Nobody does this infinitely many times. I'm not going to go get a sample of size 16 commuters forever. Chances are I do it just one time. So we are hoping that this confidence interval is one of those 95% that in the long run will capture the mean. 5% chance that this interval is bogus, that it's not accurate, and the mean is not captured inside it. Okay, and the other thing, by the way, folks, for confidence intervals, the point estimate is always exactly at the center of the confidence interval. So if you look at this 26.4, that's precisely inside of that confidence, exactly in the center of the confidence interval. Okay, so just want to point that out also. And there you have it. So I believe we are done with this lecture. We're not done with chapter 4 or week 4, but we're done with just this lecture. So I'm going to pause this, and you can actually take a break. Let's take a short recess. We'll come back and do more.